All right, so in this video, we are going to derive the C4v character table. And so to start out with these sorts of problems, the first thing that you want to do is you want to come up with an example molecule. And so C4v, the easiest thing to think about is any molecule that is square pyramidal. It's going to be C4v point group. So it doesn't really matter what we put as the atoms. I happen to know that iodine pentafluoride is a C4v molecule. So I'm going to draw that here. Here's the square part of the pyramid. And there's the apex of the pyramid. Of course, there's lone pairs on all these fluorines. And so this is a really good character table sort of to illustrate some basic principles about how character tables work. It's a little bit more complicated than simple ones like C2v or C3v. And so first we have to identify all the different symmetry operations of this molecule, or any C4v molecule will have the same. Of course, we're always going to have identity. Identity is just taking the molecule and doing it into itself. It's like multiplying everything by 1. And then we're going to have that principal rotation axis that helps define this as a C4v molecule. So we have a C4 here. And we can imagine what that C4 is doing. We're spinning it along this fluorine-iodine bond, and it's rotating one fluorine to another fluorine, and one fluorine to the next fluorine, etc. And so I use this hat notation. That means, operations. So these are all the operations. So we have E hat, we have C4 hat. We're also going to have C4 twice, okay? And so that's not going to be a 90-degree rotation. That's going to be a 180-degree rotation. 180-degree rotation is also equal to just a C2. That's a simplified way of saying it. Remember, C is 360 degrees divided by n. So 360 degrees divided by 4 is 9 degrees. That's this. 360 degrees divided by 2 is 180 degrees. That's C2. And then we also can rotate this 3 times. And that's a unique operation, right? Because that would take this fluorine and spin it all the way to this fluorine. So all of these rotations are doing different things. Now, if we did, I'm just going to write it up here in a different color. If we did a C4 4 times, that would be a 360-degree rotation, right? 490 degrees. And that would get us back to identity. So that's not a unique operation. Of course, we did C4 5 times. That'd be the same thing as C4, etc. So we've sort of used up all the unique symmetry operations that we have using this, C4 idea. What are some other symmetry elements? Well, we know C groups don't have any perpendicular C2s. Those are D groups. So what we're left with is the V part of C4V, which has to do with mirror planes. And so I just grabbed these images from the Symmetry at Otterbein website, great website to use to visualize things. And there's 4 different mirror planes. And you can see how they're cutting through the molecule. And the definitions, we have sigma V's, which are vertical mirror planes, and we have sigma D's. So here we could call it one of these sigma V's, one of them sigma V prime, and one of them sigma D, and one of them sigma D prime. Doesn't matter which one we call which. The definition of what distinguishes dihedral mirror planes, sigma D's, versus vertical mirror planes, sigma V's, is that sigma V's sigma D's bisect perpendicular C2s. So I get into that in other videos, but actually this is C point group, so there aren't any perpendicular C2s. So then there's just a convention that's used, and we call the vertical mirror planes the ones that can go through the bonds in the absence of perpendicular C2s, and the dihedrals as ones that go in between bonds. So, you know, if we're just naming things here, it doesn't matter too much. The important thing is that, or at least I don't care. The important thing is that these are different types of symmetry elements. You can see the sigma D's, they're exchanging, right? This bond is looking at itself in the mirror plane. This bond's looking at itself in the mirror plane. So it's exchanging these atoms versus this sort of mirror plane. So you're exchanging, we could call it cis atoms, right? Atoms next to one another. These mirror planes are exchanging trans atoms. So this mirror plane here, this atom and this atom are going to exchange. So we're exchanging trans atoms. So they're very different. But both of these vertical mirror planes exchange trans atoms. Both of these mirror planes exchange cis atoms. So what we can say is that the next step of all this, now that we've identified, by the way, all the operations, there's 1, 2, 3, 4, 5, 6, 7, 8 operations in C4v symmetry. Now that we've identified those 8 operations, we need to group them into classes. And the way to group those is to group them in ways that do similar things. And so we're going to group these vertical ones together. That's going to be one class. We write it as 2 sigma v. And then same thing with dihedrals, 2 sigma d's. Identity operation is always in its own class. So this is we'll call it solo class, identity and inversion. We don't have inversion in this molecule, but are always in their own class. So we have 3 classes. And so as I said, the way we're choosing these classes is by looking at similar actions that these operations do and grouping them together that way. That's not a mathematically rigorous definition. I can get into the mathematically rigorous definition in separate videos, but it can get a little bit tricky to intuit. So, you know, if you're asked to derive this a priori with no information given, you're either going to need to know that rigorous definition and apply it, which can take some time, or you're going to have to sort of memorize, you know, certain patterns, and there are patterns in the character tables in terms of how things are grouped. But you know, you might think that these 3 rotations all should go together. And in fact, that's not true. What ends up happening is the C4 and the C4-3, those are its own class. So we'll put that in 2C4. And the C2 is in its own class by itself. Okay. And sort of a hand-wavy explanation for this is that the C4 and the C4-3 are very similar in the sense that one is just clockwise rotation, one is counterclockwise rotation 9 degrees. Whereas a C2 is doing something a little bit different. It's doing 180 degrees. But again, in order to prove that, there are mathematical rules for our character tables that can allow you to know whether or not you should be putting things into the same class and not have to make these judgment calls. And so I can go over that for C4v and all the character tables in other videos if people are interested. But at this point, we have our different classes, and we have 5 classes, right? 1, 2, 3, 4, 5. So let's carry those classes over to a fresh slide, and we're going to set up our character table. And we have 5 classes, as I just said. So a character table is always in the shape of a square. So we're going to have 5 columns and 5 rows. And at the top left, we always write our point group, which is C4v. It's just convention. And we're going to have identity. Identity is usually put as the first column, although it doesn't matter. There's nothing forcing you to put these in a certain way. We're going to have our 2 C4s, principal rotation axis. We're going to have our C2 in a separate class. We're going to have our vertical mirror planes. And then we're going to have our dihedral mirror planes. So we have 1, 2, 3, 4, 5 classes, 5 columns. So we're going to need 5 rows. And right now, we don't know what to call these rows because we use Mulliken symbols, which are rules, and we're deriving the the vectors, the irreducible representations for this character table. So we don't know what they're called right now. I just give them a generic name so we can talk about them together in this video. I give them gamma. So I'm going to call them gamma 1, 2, 3, 4, and 5. All right. So at this stage, we are ready to start deriving. And there's some, and I'll put another column here in case we want to use any functions. There's some places to start out here. The best place to start out is to put ones across the board. You're always going to have a totally symmetric, every single character table has a totally symmetric representation, which is ones across the board. Okay, and so we can fill that in. The next place I like to start is to fill in, if I can, and most times you can for the simpler cases, this column. We call this column the dimensionality. And there's a rule that says the sum of the squares of the dimensionalities has to be equal to the order of the point group. The order of the point group is the sum of all the different symmetry operations. So we already know we have 8 symmetry operations because we figured that out. But just to check that, it'll be we have one identity, 2 C4s, 1 C2, and 2 each of the mirror planes, so that's 8. So the order is 8. And so the sum of the squares of the dimensionalities that are the characters under identity must equal 8. And these values under identity will always be equal to integer values, positive integers, whole numbers. So 1, 2, 3, 4, or 5. Most likely they're going to be 1, 2, or 3. Only the really highly symmetric groups are getting 4s and 5s. So you're looking at 1, 2s, and 3s. And so we already have a 1 up here, 1 squared. And so then we're going to have something like this, x squared. I'm just using variables. We have 4 more values to come up. Maybe a squared and b squared is going to be equal to 8. And so you can stare at this for a while, but if any of these is 3, remember we can't have zeros. Only 1, 2, 3 is basically allowed. If any of these are 3s, we're going to not be true because that'll bring us to 9 and then 10. So we're above 8. So we're going to have to be using 1s and 2s. So you can stare at this for a while, but basically the only way to solve this is filling in with 2 more 1s and 2 2s. Because that's going to get 1 plus 1 plus 1. Oh, sorry, 1 plus 1 plus 1 is 3. So there should be 1 more 1 here. 1 plus 1 plus 1 plus 1, that's 4. Plus 2 squared is 8, right? So that's really nice because now we can fill this part in. And so we're sort of puzzling this out with different character table rules. All right, so just for the sake of space here, I'm going to erase this part that we did. The next step, while I'm doing that, I'll tell you the next step. The next step is, well, there's a lot of different ways you could go. You could try to just puzzle this whole thing out. And that's fine. You can also try to use different functions, okay? And so what I mean by puzzling it out is you can try to use orthogonality rules. The vectors have to be orthogonal with respect to the number of symmetry elements. And I'll show you how to do that. But I like to start out with sort of when you don't have a lot filled in here, I like to start out with different functions. So let's just test different functions. So to start out, let's test the function z. And we're going to need to draw a little molecule here. So just to help us visualize things. So again, I'm going to do that iodine pentafluoride molecule. Remember, we're just doing a square pyramidal molecule as an easy C4v molecule. And so how does this function z transform under identity? Well, what does that mean, the function z? It means we're thinking about a z vector, right? So if we have our z-axis, remember O is our principal rotation axis, and then we have our x-axis and our y-axis. Can define these in different ways, but z-axis always has to be coincident with the principal rotation axis, which is our C4 right here. And then our X and our Y, I just decided to put them along the bonds. They have to be 90 degrees. But you can define this as any way. You can call this X, call this Y, left-handed versus right-handed Cartesian coordinate system. It'll all work out. Doesn't matter. But we're thinking about right now a little Z vector. And so what happens when we do these different symmetry operations on Z? Well, when we do an identity on anything, it stays the same. When we do and so the character of this, there's a 1-by-1 matrix that writes this out, right? Character means trace of the matrix, character table. So it's the sum of the diagonals across a matrix. So the sum of the diagonals across a 1-by-1 matrix is 1. So the character, I use the symbol chi of identity for this point group is 1. We just took the trace of this matrix. Every single time there's going to be a matrix here that shows this. I'm not going to explicitly write it because in this case it's just going to be simple 1-by-1 matrices. Okay, now we're on to the C4 class. We can choose, there's 2 operations there. We can choose a C4 once or a C4 3 times. We know those are the two operations in that class. I'm just going to choose the C4. And if we do a C4, that's spinning this vector around this piece of string. Well, we're in the Z plane. We're doing a C4 across the Z. It's not going to spin this. This is just, rotating it like this. We're not spinning it like this or anything. We're just spinning it. It's not going to change the vector. So that also gets us a character of 1. Let's now do C2. Well, C2 is just a C4 twice. It's very similar. It's 180 degrees. Again, it's not going to do anything. Z goes to Z. And then we have various mirror planes. So sigma V's and sigma D's. And unfortunately, these are not going to help us. The sigma D's, I can draw one here, but the sigma V's contain the bonds. So it's going to be like this mirror plane. It contains the axis. So again, that's going to be Z to Z. You're going to get a character of 1. And the sigma D, it's just 45 degrees from here, right? It's bisecting here. So that's also going to be 1. So the Z vector ends up transforming as 1, 1, 1, 1, 1. It's a totally symmetric rotation. So, I mean, it didn't do anything bad for us, but it didn't generate a new function, a new irreducible representation. It didn't solve for gamma 2, gamma 3, gamma 4, gamma 5. It got us something that we already knew. All right. So let me erase some things here, and we'll try again with a different function. And I can keep a lot of this the same. What we're going to do next is there's linear functions, there's quadratic functions, cubic functions, lots of different, those are the most common ones that are used, but also that are used are rotation functions. And so let's do that one next, and then later we'll do X and Y. So a rotation function is, let's do RZ. I want to do RZ. And so the RZ is defined as a vector, a curved vector around the axis that you're talking about. So there's RZ. It's wrapping around the Z pole. And so if we do identity on anything, it stays the same. So that's going to be a 1 for the character. For C4, well, if we define this as, here I defined it as a clockwise rotation, just my habit of drawing things. Technically speaking, let me redraw this the other way. Technically speaking, it doesn't really matter for the derivation, but technically speaking, this should be a clockwise, let's see. Oh, I actually had it the right way. Got to think about Z pointing down, sort of looking at the face of the clock, so rotating this whole thing 90 degrees in your head. But again, this is really doesn't really matter. And so here we go. That's clockwise. But just so I can make sure I'm telling you the right directions when I'm speaking, we have a clockwise rotation. C4, what that means is clockwise. okay, clockwise by 90 degrees. It doesn't really matter because C4v is also in the class, and that's going to be anti-clockwise 90 degrees. That's why I'm saying it doesn't actually matter. It's part of the reason why these are in the same class, is they behave very differently depending on how you define clockwise or anti-clockwise, right? The molecule doesn't care that fundamentally. That's just our, human thing. So anyway, though, we're doing a 90-degree rotation on this vector. And so if we think about that, we have right now how I drew it is like that. If I rotate this 90 degrees, it's just going to move this head, up a bit, and it's going to move this tail over a bit. And so I'm going to end up, if I connect the head and the tail, I still end up rotating the same direction. And because I'm still rotating in the same direction, the function didn't change. The essence of the function is the direction in which it rotates. And so I get a 1 there. Okay. Same thing's going to happen with C2. We now just rotated this 180 degrees, but again, because it's in the same direction, now if I were to think about doing 180 degrees rotation, we would rotate this, up even higher, but it's still going to be rotating in the same direction. So there's no change there. Okay, so still going in the same direction with both of these. So character is 1, so I'm unchanged. Now let's think about sigma v. So sigma v again is a mirror plane that contains the bonds. That's how we defined it. And if you look at it, I'm going to draw it through here. It's cutting this rotation vector in half. And so this side of the rotation vector is seeing itself in the mirror, and this side is as well. And so the head's going to become the tail, and the tail is going to become the head. And so we're going to get something like that. So if we look at now, we're rotating clockwise for this green vector that we started with, and the blue vector is going counterclockwise. That's something different. So RZ went to negative RZ. And therefore, the matrix that describes this is going to be a 1-by-1 matrix of -1. Sorry, this should be RZ here, technically. We had it saved over from before. So RZ equals negative RZ. So the character for that, we take the trace of that matrix, the sum across the diagonals, it's 1-by-1 matrix. So we get -1. And something very similar is going to happen with the dihedral. The dihedral is, cutting through this way with the mirror plane. That's one of them. There's 2 dihedrals, but we can choose either one. But again, that mirror plane is going to cut through. And anytime we cut through a rotation vector again like that, it's going to swap the positions of things, and we're going to get a negative. And so when that happens, the rotation vector is switching directions, so we get a negative. And so again, we're going to have the same sort of setup. The character is going to be negative. So the nice thing about this is now we've generated a new vector, and it's 1, 1, 1, 1, -1, -1. We can put that this transforms as RZ if we're just keeping track of our functions here. So now at this point, it's nice to do a check. And the check is to satisfy the orthogonality theorem. And so I want to show you what I mean by that. And so any 2 vectors in the character table must be orthogonal to one another. That means their dot product must be equal to 0. But it's an adjusted dot product that's adjusted for the number of operations in each class. And so what we're going to need to do is, in this case, let's check that gamma 1, again, we don't have Mulliken symbols named for these, but let's guess that gamma 1 dotted with gamma 2 equals 0. Let's just check that maybe over here. It should equal 0, right? And so again, adjusted for the number of classes. And so what that's going to end up looking like in terms of maybe vector notation in physics or math is we can do something like this, where we have 1, comma 1, comma 1, 5-dimensional space here, and I'm going to put a dot, and then dot it with 1, comma 1, comma 1, comma -1, comma -1. But we also have to adjust for the number of symmetry elements here. So there's one identity. So we're gonna times one of these vectors, doesn't matter which ones you do, by 1, gonna times the next component of the vector by 2, because there's 2 C4s, and there's only one C2, so times by 1, and then there's 2 each of the mirror planes. So times by 2, times by 2. So this is gonna get us 1, when we multiply this out, maybe I'll just write that in a different color in red here, a different vector, right? 1, 2, 1, 2, and 2. And so really we're dotting this red vector with this bottom black vector. And to do the dot product, we do 1 times 1 is 1, plus 2 times 1, that gets us 3, plus 1 times 1, that gets us 4. And then we had plus -1 times 2, that gets us back down to 2. 4 minus 2 is 2, plus -1 times 2 gets us down to 0. So that's 0. So it's just a good check that all this matches out. And at this point, we can actually use this sort of idea and test out some other ones. And what you notice with this, because we're normalized, and there's some patterns that comes up, because we're normalizing by the number of operations in the class when we do this dot product, you can tell that, well, look, we had to have 2 -1s here. That is a total of 4, and we had up here, the 2 -1s are under 4 operations, right? And the 2 positive ones are under 4 operations. So we can use that trick if we're going to have ones across the board and be doing -1s and 1s here. We can use that trick to help us. Now, you won't always have just simple integer values like this, but a lot of times you will on the simple character tables. So it's a good guess. And if you guess correctly, you're right. If it's orthogonal, it has to work. And so what that tells us is that, hey, well, why don't we just put a -1 here, right? And instead of having this -1 under this 2, put it under this 2 and have a positive 1 there. So then we could write something like this, right? And that's going to work out to be the exact same math. We don't know if there's a function, a simple function that transforms like this, but we don't care. We figured it out. And so that's good. All right, well, why don't instead we take this -1 and put it under the 2. And so this one now is a positive 1. And so again, we know that's going to work out. And again, if we dotted any of these with each other, it's also still going to work. So just as a test, if we dotted, there are 2 new functions, gamma 3 and gamma 4, we would write our gamma 3, and I'm going to write the gamma 3 first. So that's -1, bring space here, because we're going to be multiplying by the numbers of classes. Oops. Just write that on the right side. Ignore this one. Ignore this one. Just give me some space here. 1, 1, -1. Okay. And gamma 4 is 1, -1, 1, 1. Oops, we wrote gamma 4 wrong, because we need a negative, right? We need 2 negatives under 2 of the 2's worth of 4. So if you look at all these -1s, right? 2 -1s under worth 4 operations. 2 -1s under 4 operations. 2 -1s under 4 operations. That should be a -1 and a +1. All right, and then we have to multiply by the number of classes. One identity, two C4s, one C2, two sigma Vs, and two sigma Ds. And so if we go back into red here, that gets us 1, -2, 1, 2, -2. Now if we dot all this, maybe it can go in a different color. 1 times 1 is 1, -2 times -1 is 2, 1 times 1 is 1, -1 times 2 is -2, -2. And so now we add all these together, and we're going to get 0, which is what we want. We're orthogonal. We know our functions have to be correct. So it's very good. And you could dot all the different combinations. Gamma 1 dotted with gamma 2, gamma 1 dotted with gamma 3, gamma 1 dotted with gamma 4. All those different combinations are going to be orthogonal. Remember, but you have to normalize for the number of classes. You have to take, you have to normalize for the number of operations in each class. So that's how that works. So that's great. And we're almost done actually here. And so you could actually do the same protocol and just figure out what gamma 5 is. You could walk through this and think about what's going to make things orthogonal. I want to actually show you with the vectors with another function. So let's test, just because it shows some principles that are useful. So let's test this with another function. And I want to do the function x. So of course, x is going to go to x. And I want to draw my example molecule once again here, just so we have it. And there we are. And remember, z is defined as the principal rotation axis across just the highest order axis there is, which is C4. There's C4 here. And then my x and y's, I can define anywhere I want as long as everything's perpendicular to another. I'm going to define it like that. And now we're talking about how does an x vector transform. There's our x vector. All right, so identity does nothing. So the character, right away, we would say, well, that looks like it's going to be a character of 1. But let's keep going here and think about what x does. X, if we do a rotation, x is going to be transforming. And actually, if we rotate this way, remember we can rotate anyway because C4 and C4-3 are both in this class. We can choose either one. But if we rotate this way, x is going to go into y. It's a 90-degree rotation, right? So x actually goes into y. And that gets interesting because already at this point, if we try to write a matrix, a 1-by-1 matrix, we're going to have to start with x. We're going to put something question mark in here. How do we get y with that? We can't. There's no value, okay? So what this tells you is that x and y are linked together. And so we have to think about these together. And this automatically makes sense because we have about a dimensionality of 2. What a dimensionality of 2 means here is that two functions, any two functions have to transform together here to have this symmetry, to have the gamma 5 symmetry. So y, let's think about what y is going to transform into. So let's draw in a different color, blue, our y vector. And so our y vector is going to be there. And if we rotate that 90 degrees, we're going to end up with negative of x. Y goes into negative of x. And so now that we know that these transform together, we can actually use a 2-by-2 matrix. So we start out with xy, and we're asking the question, what 2-by-2 matrix transforms xy into y negative x, right? X went to y, and y went to negative x. And we can write that very simply. It's going to be 1, -1, 0 is on the diagonal. Okay, so review matrix multiplication if you don't know where that comes from. But what's nice is that now we can take the trace of this matrix, or the character of this matrix, that's where the name character table comes from, It's a sum across the diagonals. And so the character is just going to be 1 plus -1, which equals 0. So we can write our character, or chi is what I like to use, chi of the operation C4, or of any operation in the C4 class, could be C4-3, is going to be equal to 0. So up here, we're going to fill in a 0. And why is there a 2 here? Because now we know x and y transform together. And so the identity matrix is taking x and y and going into x and y. And so the trace of this matrix, the character of this matrix, is 1 plus 1, which is 2. So that's where that 2 came from. We puzzled it out using some other rules of the character table, but there it is. All right, let's do our C2. C2 is an 180-degree rotation. Well, that's going to spin our green vector x all the way into -x, and our y vector all the way into -y, right? Running out of colors here, but it would be -y. So we spun this y vector all the way into there. -y. All right. So now we can write our 2 by 2 matrix for that. And it's going to be 2 -1s across the diagonal. X went to -x and y went to -y. And so we end up with I of C2 is going to be equal to -2. Trace of this matrix, -1 plus -1. All right, we're almost home free here. So our next one is going to be a sigma v. We can choose either sigma v. I'm going to choose the sigma v that contains the x vector. So that if it contains the x vector, the x is in the mirror plane. So x goes to x. Y vector, here in blue, is looking at itself at the mirror plane. So it's going to flip over to the other side. It's looking at itself in the mirror, so it goes to behind. So we're going to get x goes to x, and y goes to y. We get y goes to -y, excuse me. Trace of that matrix is 0. 1 plus -1. Sigma v is 0. So that was here, and from before I didn't fill it in, we get -2. And our very last one is a sigma d. Sigma d that I'm going to draw goes down here. It splits the bonds. And x and y are looking at the mirror at 45-degree angles from one another. Remember, the dihedral splits, goes, in between the bonds. So in this point group, at least, okay, not all point groups. You have to use the more rigorous bisecting the perpendicular C2's definition to figure this out. But we don't have perpendicular C2s. So as I said earlier in the video, the dihedrals are just defined as going in between the bonds. But it's just convention. Doesn't really matter. Well, at least I don't care. So this x is actually looking at itself in the mirror plane, and it's going to transform into y. It's looking at itself at a 45-degree angle. And same thing with the y. It's a mirror plane that's going right between the two. So y is going to be looking at itself at x. So x is going to go to y is going to go to x. And so you end up with a matrix that looks like 1s on the off diagonals. And so what that does is if you take the trace of this, it's 0 plus 0. And so you end up with chi of sigma d being equal to 0. And so we got a 0. And we can put here as our functions x, comma, y. At this point, we have derived the character table. We have some functions filled in that helped us get to this point. We didn't actually have to use any of the functions to do that. We could have just thought about orthogonality and gotten there with our orthogonality rules. And it helped to, set up knowing that the first one's going to be 1s across the board. And we had this dimensionalities where the square of the dimensionalities equals the order of the point group. That was nice. The only thing left to do is to assign the Mulliken symbols. And that's pretty trivial. I'll just pull up what we have here. You can see we did this correctly. Everything is looking nice. There's our x and y. It turns out the rotation vectors also transform together. We use these parentheses to show that they transform together. We could have done quadratic functions. Maybe I'll show you one of those in a different video how to do that. But for now, we're all good, and all we have to do is fill in these Mulliken symbols, and there's simple rules for that. And so we can go over them right now. We had all these vectors, right? And so anything with a dimensionality of 2 is going to be given an E. So that one's simple. And there's no inversions in this point group, which is where you have to talk about Garada or ungarada, G's and U's. So none of these have G's or U's. And then if we have a dimensionality of 1, we're going to give it an A or B. So you can see all the ones with 1s have A's or B's. And then the first thing to do is look if we're symmetric with the principal rotation axis. If we are symmetric, we're going to give it an A. So the plus 1s got A's, the minus 1s under the principal rotation axis was the C4, the highest order, the highest n value, n equals 4 of the point group. The negative ones, the anti-symmetric ones, those get B's. So that's a nomenclature there for the A's and the B's. And then lastly, we look at mirror planes. And we look at the vertical mirror planes. Those are sort of the ones, just by convention, we do first. So if we're symmetric with the vertical mirror plane, we're going to give it a 1, subscript 1. So plus 1 there, there's A1 and plus 1 here, B1. And then if we're anti-symmetric with the vertical mirror plane, we'll give it a 2. So negative 1 there, B2, negative 1 there, A2. And so that's it.